Howdy, I'm back. In this video, I'm going to be talking to you about section 6.2, which is bond polarity. So let's get started. All right, so like we know, in a covalent bond, electrons are attracted to both nuclei. So they're shared between the two nuclei. But sometimes one nucleus attracts the electrons more strongly than the other. So sometimes the electrons end up being closer to one of the nuclei than the other. When this happens, the bonding electrons are closer to one nucleus, which creates an uneven distribution of electron density. Remember, we talked about electron density way back in chapter 3 when we started talking about the probability of where to find an electron. So that's basically the electron density, the probability of where you're going to find that electron. So now we have an uneven distribution of that probability. So the electron is more likely to be found closer to one nucleus than the other. So it's not equally shared between the two. And this is what we call a polar bond or a polar covalent bond. So that both terms will be used interchangeably. So let's look at what that means. So down here, this is from your book, we have the H2 molecule, the HF molecule, and the sodium fluoride molecule, so NaF. So we can see the whole spectrum here. When electrons are shared equally, or they're equally attracted to both nuclei, we call that a nonpolar bond. And that's what we see here with the H2 molecule. So hydrogen and hydrogen are the same. So both hydrogen atoms share those electrons equally. And we can see the electron density is where we have the red color. Blue is the low electron density, red is the high electron density. And we can see that for H2, the electron density is uniformly in between the two hydrogen atoms. So the electrons are shared equally between the two. They spend the same amount of time close to each nuclei. So we end up with a uniform electron density where it's highest in the middle between the two nuclei and lowest on the ends of the molecule, because there aren't any other electrons in the H2 molecule, just the two that are in the bond. We don't have any lone pairs, so on the other side of the nucleus, away from the bond, we have a low electron density. Now let's look at HF instead. So hydrogen fluoride, or the hydrofluoric acid molecule, has an unequal or an uneven distribution of electron density. So we see that the electrons spend most of their time over here, and this is the fluorine side of the molecule. And the hydrogen side of the molecule, the electrons don't spend very much time over there at all. So we have blue, which means low electron density on the hydrogen side of the molecule. Increasing electron density in between. So the electrons still spend a good amount of time in between the two nuclei, but they spend most of their time, it's most likely to find them on the fluorine side of the molecule, so closer to the fluorine nucleus. So we could see the uneven distribution. It's not shared in between the molecule anymore. It's focused on one side of the molecule, focused on the fluorine nucleus. And that's why we have high electron density shown in red. And then if we look at sodium fluoride is a metal and a nonmetal. So sodium fluoride is an ionic compound. It's not a covalent compound, so it's not a polar covalent bond. It's an ionic bond. And we'll talk about that difference a little bit more in a few slides here. But sodium fluoride, because it's an ionic compound, we see a really extreme difference in the electron density. So the electron spends basically no time, pretty much none at all, on the sodium side, and almost all of its time over here on the fluorine side. So that is what we would expect, because when we have an ionic bond, it's a transfer of electrons from the sodium, or from the cation, sorry, the cation, which is sodium in this case, to the anion, which is fluorine in this case. So we transferred the electron, so that makes sense as to why we would never, almost never, see the electron on the sodium side, and almost always see the electron on the fluorine side. So it's not, so hydrogen fluoride, we had a kind of, it was an uneven distribution, but still a sharing of electrons. Whereas when we look at sodium fluoride, they're not really sharing at all. Fluorine is taking the electron density almost completely onto itself. But just like we learned with probabilities of where to find the electron, there's not a 0% chance of finding the electron on the sodium side. So there's still some green in between the two, where there's a possibility of finding the electron shared between the two and not just all on the fluorine side. So it's a spectrum. Sodium fluoride is an ionic bond. It's an ionic compound, but there is always some probability that the electron would be away from the fluorine nucleus, just based on probability, just based on, you know, random happenstance. It's an outlier. It could be found on the sodium side. And then this over here is just a different way of representing electron density. This is the water molecule, as we will become very familiar with in the next couple chapters as to why it looks the way that it does. But you can see the positive side of the molecule, where the electron doesn't end up hanging out very often, is the hydrogens, and oxygen takes the electrons more onto itself, and that's why it's red. So instead of having green in the middle, we have white in the middle, but it's the same concept. So higher electron density on the oxygen atom, lower electron density, and hence a more positive side if it has less electrons on the hydrogen ends. So we will understand that a little bit better in a few slides as well. Alrighty, so this is how your book shows it. It's a spectrum from purely covalent bonds or nonpolar bonds to ionic bonds, which, so we have very equal sharing of electrons, to basically no sharing at all, where we have oppositely charged ions because we had a basically a complete transfer of the electron from the cation to the anion. And then in the middle here, we have these polar covalent bonds. So we're going to see that there is something in between these covalent molecules and ionic molecules, and those are polar covalent molecules, or polar covalent bonds, where we have partial charges, as we'll explain in a little bit here, and unequal sharing. So the term polar refers to the existence of a dipole. So a dipole means there's two different poles, kind of like the Earth. We have the North Pole and the South Pole. In these molecules, we have two poles as well. We have a partial positive pole and a partial negative pole. And the partial charges on these ends of the molecule, or the ends of the bond, I should say, are given with this little delta. So delta plus and delta minus for the partial positive and partial negative charges on the bonds, or on the atoms on either side of a bond. Dipole is characterized by the dipole moment, which I'll explain in a little bit, but it's the measurement of the strength or the polarity of the dipole. So we can actually measure the polarity of the molecule, as we'll see in a little bit. And that dipole moment is proportional to the magnitude of the charges and the distance between those charges, following Coulomb's law, as we have become very familiar with over this semester so far. So I will explain this notation. We have the partial positive and the partial negative, and we have this funny looking arrow between our two atoms. I'll explain that in a little bit as well. So why are electrons shared unequally? Why do some nuclei pull the electrons closer to themselves than others. The ability of an atom in a molecule to attract electrons to itself, shared electrons in particular. So it's attracting these bonding electrons to itself. So we're always talking about these electrons in a bond now, is referred to as electronegativity. So a few of you asked a while ago about the differences between electronegativity and electron affinity. They're very similar, but electronegativity refers specifically to the ability of an atom to attract electrons from a bond, not electrons when that atom is by itself in the gas phase. So when that atom is by itself in the gas phase and you're trying to add electrons to it, that is electron affinity. When an atom is attracting electrons between itself and another atom, that is electronegativity. So atoms with a high electronegativity attract a high electron density. So if we look back on this slide here, where I introduced the idea of polar bonds and electron density, the atoms that have the high electron density near them, so like oxygen in this water molecule and fluorine in hydrofluoric acid or hydrogen fluoride here, those atoms have the higher electron density to them and or near them, and that's because they are the more electronegative of the two atoms in the bond. So oxygen and fluorine are both more electronegative than hydrogen, so they pull the electrons closer to themselves and further away from the hydrogen. Alrighty, and we can see that here. This is a periodic table showing different electronegativities. So the highest electronegativity is fluorine with an electronegativity of 4. There are no units on electronegativity. Electronegativity doesn't really mean anything, to be honest. It is just a relative comparison of the ability to attract electrons from a bond. So they are all relative to one another. Fluorine has a really high electronegativity compared to hydrogen or sodium or whatever. It's all relative in the case of electronegativity. So fluorine has the highest. Oxygen and nitrogen and chlorine are the next highest. And then we start to go down from there. Carbon, sulfur, bromine, and iodine are the next highest. And then we go down from there. And the lowest electronegativity are down here in the bottom left. And that is related to our periodic trends. So it's pretty much just like electron affinity, except now we're talking about the ability to attract electrons within a bond. So it's got the same trend. It's higher. We got high electronegativity to the upper right of the periodic table, low electronegativity on the lower left of the periodic table. And that is related to effective nuclear charge and atomic size, just like electron affinity was. So here's some notes about electronegativity. And again, I'm using old slides, so it should be group 18 and not group 8, sorry. The noble gases, group 18, are not assigned electronegativity values. So you can see they're not even on this table. There should be something here, group 18 or 8A in the old style. It's not even there because noble gases don't get electronegativity values. Noble gases don't usually even form bonds, but when they do, they have no electronegativity. Whatever else is in the bond pulls the electrons completely away from the noble gas. They have no electronegativity. Other notes, electronegativity increases as we go left to right and as we go up. So it decreases as we go down and to the left. And this is the opposite of atomic radius, if we remember back to the trends in atomic radius. So the biggest atoms were down here in the lower left, or the southwest, as one of your classmates put it. Those are the biggest atoms because they got more electron shells the further down we go on the periodic table, and a lower effective nuclear charge when we're to the left of the periodic table. So the biggest atoms are the ones that don't really attract electrons towards themselves. They don't have a lot of effective nuclear charge. The electrons would be far away from the nucleus, so they wouldn't be attracted to that positively charged nucleus very well. Up here in the upper left, instead, we have the smallest of the atoms, and that means that when they are interacting with electrons in a bond shared between them and another atom, they're tiny, they have a tiny atomic size, so the electrons in the bond can get really close to the nucleus and feel that positive charge. So that's what happens. Those electrons are attracted to the nucleus because they can get closer to it because we have a smaller atomic radius. So electronegativity is inversely related to atomic radius. Hydrogen doesn't follow the periodic trend really because it's a little weird. Hydrogen would kind of be close to helium over here. Remember, we've learned that hydrogen can act like a group 1A, or a group 1 element, but sometimes it also acts as a group 7 element. So it's kind of in between with electronegativity, which is what you might expect. I mean, it doesn't follow the periodic trend, but based on the fact that we know it acts a little bit like group 1 and a little bit like group 17, it's somewhere in the middle when it comes to electronegativity. So it's pretty close to boron and carbon. All right, and metals generally have low electronegativity values. Your book actually mentions that the increasing metallic character of an atom results in lower electronegativity. So metals generally have low electronegativity values. Nonmetals generally have high electronegativity values. And we can see that we're around 1 or even less than 1 over here in the main group metals. And we're usually around 2 or higher in the nonmetals category. And just to keep in mind, fluorine, oxygen, nitrogen, and chlorine are our most electronegative elements. And I just wrote all over that, sorry. But fluorine, oxygen, nitrogen, and chlorine. So our gray and yellow ones here are our most electronegative elements. Alrighty, so I've sort of mentioned this, but the polar or ionic character, depending on, how big the difference is between it, or how much one atom will attract electrons compared to the other, that polar or ionic character of the bond is related to the difference in electronegativity between the two atoms. So when one of the atoms has a really high electronegativity and the other one doesn't, then that one with high electronegativity is going to really attract the electrons from the bond towards its nucleus. So there's going to be a lot more of a difference there. So the more uneven the distribution of electron density, the more polar or even ionic the bond is. So a bond between atoms whose electronegativities differ by less than 0.5. So if we look at the electronegativities and we subtract them and we get a number less than 0.5, we generally consider that a purely covalent or nonpolar bond. So for example, if you look at two atoms that are the same, like if we look at fluorine and fluorine, fluorine is a really electronegative atom, but when it's bonding with itself, when it's bonding with another fluorine atom, the difference is 0. So that's a purely covalent bond. Both of those fluorine atoms really want those electrons to be close to them, but they're both equally electronegative, so the electrons still actually end up being shared equally between the two because they both pull just as hard. It's like two really good tug-of-war teams against each other. So that's considered a purely covalent or non-polar bond. When there's a bond between atoms with electronegativities differing by 0.5 to between 0.5 and 2.0. So if we subtract the two electronegativities and we get a number between 0.5 and 2.0, we consider that a polar or polar covalent bond. And if we subtract the two electronegativities and we get a number that is 2 or bigger, then we consider it an ionic bond. So if we look back at our periodic table here, for example, if you look at sodium and fluorine, fluorine has an electronegativity of 4, sodium has an electronegativity of 1, we subtract them, we get 3.0. That is an ionic bond, like we said on the first slide in this video. If we subtract like hydrogen and carbon, so carbon is 2.5, hydrogen is 2.1, the difference is only 0.4, so that's pretty much a nonpolar bond. I mean, there's still some electronegativity difference, so there might be a little bit of more attraction towards carbon, but we consider it basically a nonpolar bond. So that's the difference. So really big electronegativity differences would be metal to nonmetal, and then smaller electronegativity differences would be nonmetals versus other nonmetals. So basically what we expected, a metal and a nonmetal form an ionic bond, which is what we learned way back when in chapter 5, not that long ago, I guess, but way back when. And nonmetal with nonmetal is a covalent bond, which we learned back in chapter 5 as well. But now we can differentiate a little bit, and depending on the electronegativity difference, we can say whether it's a polar covalent bond or a nonpolar bond. So we could specify a little bit more. We can learn a little bit more about the bonding. Alrighty. So here's some examples. The polarity of a polar covalent bond. So the polarity is kind of a range. It's a relative term, I guess, of a covalent bond is related to the difference in electronegativity. So it's the polar character of the bond. So let's look at some examples of polar covalent bonds. If we look at HF, CF, and OF bonds, we can look at the difference in electronegativity. So fluorine is 4.0, so it's going to be the same for all three. But hydrogen is 2.1, carbon is 2.5, and oxygen is 3.5. So the difference is 1.9, 1.5, and then only 0.5. So when it's between 0.5 and 2.0, they are polar covalent bonds. So all three of these are polar covalent bonds, but the difference in electronegativity tells us how polar the bond is. So the higher this number, the closer to 2, I guess, the higher this number, the more polar the bond is. So HF is the most polar of these three bonds, and OF is the least polar because there's only a 0.5 difference. So in terms of polarity, HF is more polar than CF, which is more polar than the OF bond. So we're increasing in polarity from OF, CF to HF. So increasing in polarity as we increase the difference between the electronegativities. Hence, for all three of these, fluorine is the more electronegative atom, so the electrons in the bonds shift towards the fluorine atom. They shift more towards the fluorine atom with the HF bond than with the OF bond, but they're still shifting. So we draw our partial charges. Fluorine is going to have the partial negative. It's going to be where most of the electrons are found. So electrons are negatively charged. That's where we find the partial negative charge. If the electrons are being pulled away from the other atom, which could be hydrogen, carbon, or oxygen in this case, if the electrons are being pulled away from that atom is going to have a slightly more positive charge. And we're going to be able to draw that with this arrow. So this arrow designates the polarity of the bond. The positive end is this little positive sign on the end of the arrow, and the negative end is the point of the arrow. So, like I said before, we can have a quantitative measurement of polarity, and that's called the dipole moment of the bond, and that's measured in units of debye. So, just so you know, it's units of debye. So this is our polar bond again. We've got the positive end with the little positive part on the arrow, and then the negative end of the bond is where the arrow points towards. So how do we calculate a dipole moment? It's a quantitative measurement, so we can calculate it. We can also measure it experimentally. So it's calculated by multiplying the magnitude of the charges in coulombs. So capital C for coulombs, that is, so as we've learned, Coulomb's law tells us about charges and whatnot. He actually has a unit, an SI unit named after him called the coulomb, which is a unit of charge. So coulomb, so we have the magnitude of the partial charge on each atom in coulombs, and that's multiplied by the distance between the two atoms, which is also known as the bond length. So here we have a little table from your book which shows bond lengths and dipole moments of some different bonds. So HF, HCl, HBr, and HI. So as we go down the periodic table, our atoms are getting bigger, so the bond length is getting bigger. So hydrogen's the same for all 4 of these, but iodine is bigger than bromine, which is bigger than chlorine, which is bigger than fluorine. So as we get bigger going down the periodic table, our bond length also has to grow, the distance between the 2 nuclei. And as we get bigger going down the periodic table, our electronegativity is decreasing, because the bigger the atom, the less it's going to attract electrons, because those electrons are going to be further away from the nucleus. They're not going to feel that positive charge. So the bigger we get, the smaller the electronegativity, which means we have a less polar bond, because HF, so HF has a big difference in electronegativity, so that's because fluorine is more electronegative. And then we go down to chlorine. Chlorine is less electronegative than fluorine. So the difference is smaller between chlorine and hydrogen's electronegativities. We go further down. Bromine and iodine are less electronegative than fluorine. So the difference between them and hydrogen is even smaller the further we go down the periodic table. And we can see that in the dipole moment. So the dipole moment, like I said, is a measurement of the polarity of the bond. And as we go down the periodic table, our bond length increases and our dipole moment decreases. So the polarity of the bonds decreases. We can also, so if we use the experimentally measured dipole moment of a bond, and we compare it to the calculated dipole moment if we assume ionic bonding. So what that means is that we assume, so for example, if we assume that HCl, this bond, instead of assuming partial charges, we assume discrete charges. That's what it means in this equation. So if we'd assume discrete charges instead of a partial negative and partial positive like we know exists between this bond, if instead we assume that it is a full positive, a discrete positive charge and negative charge, so if we assume ionic bonding where the electron is transferred from hydrogen to chlorine, making a cation and an anion instead of partial charges and sharing of the electron. So if we assume ionic bonding instead and calculate that dipole moment, that is the ionic bond, and we put the experimentally measured dipole moment on top, which is going to be smaller because we know it's actually a polar bond and not an ionic bond. We put that on top and multiply by 100. That gives us what we call the percent ionic character of the bond. And this little graph from your book actually shows you the percent ionic character versus the difference in electronegativity between the atoms. So the bigger the electronegativity difference, like with lithium fluoride or potassium fluoride, which are both very ionic bonds, so they have a very high electronegativity difference, and we see that they have a very high percent ionic character. So they're very ionic. Whereas when we look at these smaller ones down here, like HI, HBr, HCl even, there's a smaller difference in electronegativity, like I said on the previous slide. So there's a smaller percent ionic character. They're less ionic. They're more covalent, which makes them polar covalent bonds. Okay, so that's a little confusing. So I would suggest reading the book and watching this in, I don't know, slow motion. But hopefully that helps a little bit with me trying to explain it to you. And I'll see you guys in class tomorrow.